we saw circuits, right? And we know that electricity is the flow of electrons around a circuit. So here we've got a circuit, there's electrons going in a circle and they're flowing, right? But there's a lot more to electricity than that, right? So what I see is we've got a battery, we've got the wire, and we've got the lamp or the light bulb, and they represent three different things, okay, that are a part of electricity. The first is battery. And the battery represents voltage, and voltage is measured in volts, right? 9-volt battery, and it's like the electron pusher. So it's the thing that's like pushing the electrons through the wire. Okay, it's what's pushing the electrons through the wire. The wire itself, that's where the current is, and the current, just like in a current of water, is like the flow. Okay, and so the current here is the flow of electrons. So if there's a large current, there's a lot of electrons flowing. If there's a small current, then there's not very many electrons flowing. Okay, and it's measured in amps. And then finally, we have the lamp, or the light bulb, and this is the resistor. And so it's measured in ohms, and it's what uses the energy of the electrons. It's the thing that sucks up the flow of the electrons. So, if you've got a motor that turns a fan, that's a resistor. If you've got a lamp that gives light, that's a resistor. If you've got something that heats up from electricity, that's a resistor. So whatever's using the electrical energy, that a lot of times is the resistor. Okay? And this is how I like to think about the relationship between voltage, uh, current, and ohms. So voltage is pushing the electrons through, right, in the form of amps. And the resistance is what's cutting off the amp, right? So the more resistance there is, the more that the current is going to be squeezed, because the more this resistance needs, more electrons this resistance needs. And so we have this Ohm's law, which is pretty simple, which is voltage equals resistance times current. So whatever this times this is, it needs to be equal to this, right? So you can't have more resistance and current than there's uh, something to be pushing those electrons through the circuit. So the more voltage there is, the more current there can be, and the more ohms there can be. Okay. Now, we're going to look at circuits in series. Circuits in series. So let's take a look at this. And circuits in series is what we have here. Okay? On the top, we've got a battery. We've got these little spheres represent electrons, and we have a resistor, which is a light bulb, and we connect it, and it shines. And you notice how brightly it's shining right now. Okay? Now, what happens if we put in another light bulb? Well, let's see. Another light bulb. All right. If you notice, the light bulb is bright, right? So now they're sharing the electricity. The light bulb is half as bright. Okay, there's twice as much resistance, and there's half as much current. Okay, so great. Those are the characteristics of a circuit in series. Now, look what happens if I break the wires, right? If I break the wires, or if one of these light bulbs were to suddenly go out, everything goes dark. There's no more current running. There's no more electricity, and none of the light bulbs are lit up. Okay? Now that is different than circuits in parallel. Circuits in parallel are a whole different thing. Okay, so let's check out circuits in parallel. We've got our simulation. I hook everything up. Now notice both of the light bulbs are equally bright. Okay, so that means that because the electrons are being split in two different ways, they're lighting up the light bulbs equally brightly. Now you won't know why that is until you get to high school, or you can look it up online if you want. But we're not going to worry about that too much right now. We're just going to worry about the characteristics. Now check this out. If I break this wire here, if this light bulb goes out, look what happens. The other light bulb still works. So that's one of the characteristics of a circuit in series. Okay, if I reconnect it, boom, looks good. Same thing here. If I split this, the other one is still working. Okay, so that's one of the characteristics of a circuit in parallel. Now, think about what kind of circuit would you want to use for Christmas lights? Christmas lights are a string of lights. There's tons and tons of them. Would you want a circuit where if one light bulb goes out, all of the light bulbs go out? Or would you want a circuit in which if one of the light bulbs goes out, that's fine, all of the other light bulbs still can function? Okay, so think about that and think about whether or not that would be circuit in parallel or a circuit in series. If you have any questions, let me know. Send me an email, and I will be happy to answer them. Good luck.